And first, let's create a parent set which will record node and the parent. And now let's start with 0, and we record its parent is -1 because 0 is the root node and we represent them in the graph. And then we'll create a list queue which will first start with a 0. It will check the elements we want to check for later, and we use a while loop. Only the queue exists, we will execute. So first, let's dequeue 0 from the queue, and we pop left them into node. Now the node available is 0, and we check the neighbor of the node 0, which have 3 neighbor, 1, 2, 3. So first, let's check neighbor 1. We record node 1's parent is 0, and we append 1 into the queue, and then we check neighbor 2. We record node 2's parent is 0, and we append 2 into the queue, and then we check neighbor 3, and we record node 3's parent is 0, and we append 3 into the queue. So first, we pop 1 from the queue into the node variable. So now we check node 1, which have 2 neighbor. First, we check neighbor 0, which is equal to 1's parent. So we use continue to skip this trivial cycle. And then we check neighbor 4. We just record node 4's parent is 1, and then we append this 4 into the queue. We pop 2 from the queue into the node variable. Now we check node 2's neighbor, which is 0, which this neighbor is equal to 2's parent. So we use continue to skip this trivial cycle. And then we pop 3 from the queue into the node variable. Now we check the node 3, which is the 0 neighbor, which is also equal to 3's parent. So we use continue to skip this trivial cycle. Now let's pop 4 from the queue into the node variable, and we check the neighbor 0, which is equal to 4's parent. So we use continue to skip this trivial cycle. Now since the queue is empty, so we break up the while loop, and then we check the length of the parent, which is 5, which is equal to n nodes. So we return true because it is fully reached the graph. So first, let's create a set parent. We first put the 0 node, which is our root node, so we let the -1 become its parent. And then we create a queue, and we just dequeue from the collection. Dequeue 0 from the collection, and then let's start a while loop while queue exists. Every time we update the nodes from the queue just by pop left an element from it. So after we update nodes, we use a for loop for neighbor in adjacency list as nodes. So this will iterate every neighbor in that node, and then we update our parent set by writing an element neighbor's parent is node, and then we update our queue just by append the element from the neighbor. And before that, we should consider the edge case. If the neighbor is equal to parent node, that means this node is not only neighbor but also the parent of that node. In that case, you will form a biconditional edge, which is a trivial cycle, so we use continue to skip that. And another edge case is the neighbor is already exists in the parent. That means it already checked before. If it already checked before, it will form a cycle. If it contains a cycle, we will return false, because a tree must not contain a cycle. And after we finish this while loop, we just return the length of the parent and compare it with n. So if it equal to n, that means we already checked the same amount of nodes, which is equal to the entire nodes. That means we are fully reached every node in the graph, so that is valid tree. Let's analyze time complexity. First, we let the capital E represent how many edges we have, and then we let the capital N represent how many nodes we have. Then we're creating the adjacency list. It requires us to initialize a list of length n, so it contains n node sublist. It will cross O of n time, and then we're iterating over the input list edges and inserting E edges into the adjacency list, so it crosses O of E time. This gives us O of E plus O of n, which is O of n plus E time. So each node is added to the data structure once. This means that the outer loop will run n times. So for each of the n nodes, its adjacent edge is iterated over once. So in total, this means that all of the E edges are iterated over once by the inner loop. So therefore, it gives us our total time complexity is also O of n plus E times. And because both parts are the same, so we get the final time complexity, which is 2 multiplied by O of n plus E, which is O of 2n plus O of 2e, which is asymptotically equal to O of n plus E time. Let's analyze space complexity. The adjacency list is a list of length n, so it contains n nodes, and inside it, the inner list is with the lengths that we added to. Total of them is E, so this gives us a total of O of E plus n space. And we should also consider the worst case, the data structure stack or queue will have all n nodes on it at the same time, so it's giving us a total of O of n space. So in total, this gives us O of E plus 2n space, so asymptotically equal to O of E plus n space.